Welcome you all to the technical session of day 1. Expert of this session, we have Professor A.K. Rathore sir. Before inviting him, let me take the privilege to give a brief introduction about him.
Yeah, keep it short.
Okay, sir.
Yeah, 2-3 lines. Yeah.
Professor Akshay Kumar Rathore sir received the master degree in electrical machine and drive specialization from IIT BHU Varanasi, India, and PhD degree from Power Electronics from University of Victoria, Canada in 2008. His research interest includes the analysis of design of novel current fed converter, soft switching design, and modulation scheme of DC-DC converter and multi-level inverter. He was the recipient of gold medal of securing the highest academic standing in his master degree. He was also the recipient of 2013 IEEE IAS Andrew W. Smith Outstanding Young Member Achievement Award, 2014 ISAO Takashi Power Electronics Award, 2017 IEEE IES David Irwin Early Career Award, 2019 IES Publication Service Recognition Award, 2020 IEEE IES Outstanding Area Chair Award, 2020 IEEE Vimal Bose Award for Industrial Electronics Application in Energy System, and 2021 Nagamori Award. He was recognized as Distinguished Alumni Award in Young Achievers category from IIT BHU Varanasi in 2023. Thank you, sir, for taking our invitation. Now over to you, sir.
Can you see my screen now?
Yes, sir.
Yes, sir.
Yes, sir.
All right. And slides are moving.
Yes, sir, it's
Yes,
moving.
yes.
Slides are moving, right?
Yeah, yeah.
Okay. Yeah, that's fine. Yeah, I always ask this because sometimes it gets stuck in Google Meet, especially. Okay. Probably 1 hour 20 minutes or 1 hour 10 minutes. I will just deliver some basic and advance of investment in chargers. So we go through some basic classification first, and then I show you some new technologies that we also developed in our laboratory, which is very simple actually, because my research so far has been very simple. I mean, if you see, you might have heard in the bio that I published mean basically my students published, right? My students published around 300 plus paper that includes around 110 ITP transactions. And 110 is possible in 10 years, provided you are doing simple research rather than complex, because complex research, first of all, cannot be published and it takes time. So mine has been quite simple and but impactful. Important thing is impact. It need not to be complex. It should be simple but impactful. So we will just discuss that. So this is just an overview that we just go through classification of EV charges very quickly, and discuss some potential EV charging system and power electronics, role of power electronics in EV chargers, because EV charger is power electronic itself, right? What is EV charger? EV charger is AC to DC converter. AC, basically the power that you are taking from the AC outlet, and DC because the battery is DC. So you need to feed the DC current to the battery. So electric vehicle charger is power electronic device which is AC to DC converter, or in other word we can say rectifier. Okay, so charger is a rectifier unit. Only additional things that we require is sensors, communication bus, CAN bus system, etc. to start and stop, and sensors to control the battery temperature, etc. Okay, but the major part that controls the charging current, the major part that controls the power flow, the high power or low power, these are all power electronic system actually. Okay, yeah. Okay, so transportation electrification is picking up, I mean, all over the world, and we are one of them. and it is going to open scope in India quite a lot, because I think we are the third largest country in the world with the using highest number of vehicles. I think number of vehicles, not electric vehicles, okay, number of vehicles in India around 23 crores actually, if I'm correct. And right now, the electric vehicles in India are very close to between 1 or 2 crore. Nobody knows the exact number, but between 1 to 2 crore. Okay, so what we can see is that the electrification so far in India is less than 10%. Okay, so let us say probably 6 or 7% only. Okay, so still we have a long way, another 93%. Okay, another 93%. So that opens up scope for us. Okay, now electrification. Now, right now we are talking only ground electrification. If we talk about like electric ship, which is sea, and if we talk about more electric aircraft, which is space, okay, then technologies will be different. Okay, but in ground electrification itself, we have multiple opportunities. Okay, not everybody has a car, then electric bike opens up a scope. Okay, recently I was talking to Vice President of Maruti Suzuki. He visited us in Mangalore for PEDES conference, and he was with me in Bhubaneswar KIT University for STPEC conference, as well as in Varanasi for EV conclave. And we both are the founders of AICTE India, also Transportation Electrification Conference India. He was mentioning that number of two-wheelers are more in India than number of four-wheelers. Okay, nobody pays attention to power supplies of two-wheelers, a startup for two-wheelers, or charger for two-wheelers. Everybody is focusing on basically electric car, electric taxi, EV chargers, traction inverter, but more opportunities for basically two-wheelers. Okay, because users are more. And further, we see that local transportation is quite important and busy in India. People use auto, people use rickshaw. So now if you see this trio, okay, this comes from Mahindra, okay, and this e-rickshaws, which are very popular nowadays in Jaipur and many other places for short distances. And e-rickshaw length, I mean the e-rickshaw driving range can be increased by solar panel shading basically. Okay, like suppose India is a solar rich country, Jaipur, Tamil Nadu, Mumbai, Kerala, right? Where sun is available throughout the year, and this sun kind of shading can help basically providing shadow convenience to the passengers, as well as it is continuously charging the vehicle battery of e-rickshaw. So that way the driver can go longer rather than after 4 to 6 hours, then they go back, charge and come back. So this 6 hours can become 7 hours basically having solar to vehicle battery charger. That we will see actually. Okay, so this opens up scope for electrification in India rather than just focusing on four-wheeler. Okay, yeah. Okay, now chargers could be several types. Everybody focuses on like 3.3 kilowatt charger or basically 7 kilowatt charger, because 7 kilowatt is the limit for single phase and 3.3 kilowatt is for onboard chargers that you can put inside the car, because it does not take much space or volume is less, cost is less. So vehicle cost will not increase much. So 3.3 is very popular for onboard charger. But when it comes to off-board single phase charger, the limit is 7 kilowatt, or some companies use 7.4 kilowatt. Okay, yeah, because there is the limit for single phase. If you want to go further, then you need to use three-phase power supply. Okay, but if we start like laptop adapter kind of chargers, okay, so I don't know how many of you are aware now that China is even making the mobile charger 120 watt. Somehow I left that charger in my living room, otherwise I could have showed you actually. So I can charge my mobile phone actually just in 15 minutes. Okay, I'm using the same charger now for my laptop charging also, because the laptop charger that is given to me by HP is 65 watt, but the one I'm using is 120 watt. Okay, so it can be charged very quickly. So that is kind of fast chargers, but that is still a portable chargers. Okay, so these portable chargers are already coming in the range of 100 to 300 watt. Okay, you can keep in your bag. Okay, very easily, and it is nothing. It is basically AC to DC converter. This is AC, right? This is AC, and this is DC. And nowadays, this DCV is coming in the form of C type. Okay, coming in the form of C type, and this is portable and conductive. Okay. Yeah, this is another one that is quite popular for e-rickshaw. They have basically this under the seat of the driver. Okay, this is up to 500 watt, and I think you can get this in 3,000 to 5,000 rupees based on the functionalities you want in your e-rickshaw charger. Okay, of course, the same can be used for your cars also, because in India the cars are also 48 volt, and e-rickshaws, the trios are also 48 volt. The same can be used there as well. Only thing is that for electric cars, we are not having the uh, connector, the charging gun or connector like a simple electrical plug. You might have heard the CCS2 charger, right? CCS2 chargers. So that's why we cannot use this for electric car as it is. Okay, but these chargers are quite popular in the range of half kilowatt. Okay, yeah. Now, if we see from e-rickshaw to electric car, and I was explaining that there are onboard chargers which is approximately 3.3 kilowatt because of the cost, volume, and weight limitation. And then this is fast charger, which is DC, which is also known as a DC charger, because its capacity is 3.3 kilowatt, but here the capacity is more than 50 kilowatt. That can go up to megawatt in future. Already in Singapore, we started talking about megawatt charging. Okay, so megawatt charging does not mean that one vehicle will get the megawatt. You can have a charger of megawatt, you can use into a modular stackable form, and each can be 100 kilowatt or 50 kilowatt, and at a time, one system will be able to charge very fast 10 or 20 vehicles. And even it can do 40 vehicles, provided once those 20 vehicles have reached 70% capacity, then you reduce their power and then they give more power to another 20 vehicles basically. So these are charging strategies based on the modular DC fast chargers, one single unit of 1 megawatt. Okay, so this also opens up scope basically for a different levels of charging and different charging strategies. Okay, yeah. Right now in India, I think it is limited to 100 kilowatt, but ABB and others like Schneider, they have moved up to 500 kilowatt, I believe. And then, so 500 kilowatt means half megawatt already. And very soon it will reach to 1 megawatt and beyond, because it will have the capacity to charge a fleet of vehicles. Okay, a fleet of vehicles altogether. Okay, so because of high capacity, large volume, weight, and cost, it is off-board charger. But it has the capacity to charge your EV in 30 minutes, while on-board charger takes around 6 hours. Okay, yeah. Similarly, like so far we were discussing the conductive or plug-in charger so far. Similarly, there is a possibility of wireless charging. So you can see in wireless charging that, so here is the CCS2 charger, that's what I was mentioning, that we do not have a normal wall plug basically. The charger, the connector for EV charger is different compared to the mobile and the laptop. The reason is basically safety. The reason is the requirement of sensors and communication system. Okay, yeah. And in addition to plugins, you see there is a wireless charging, in where what happens that half of the part like this is divided into two. One part is on the ground and another part is basically on the car. Okay, so that way you can reduce the cost and weight of the onboard EV chargers on the car. Okay, as well as it will cause you convenience of charging. Okay, it can be stationary charging, it can be dynamic charging. Okay, Oak Ridge National Laboratory has tested both. They have tested dynamic wireless charging also. So when you are driving, you can charge, provided the road track has basically this kind of coils after every few kilometers. Okay, then you can do the bulk charging, and then your vehicle will not have any kind of range limitation. Right now, suppose in India the vehicle has a limitation based on the model you purchase from 100 kilometer to 300 kilometer. That range anxiety will be over if after every few kilometers, if you can do bulk charging through wireless charging. Okay, similarly in countries like Western countries where snow is a problem, the drivers cannot come out actually in heavy snowfall and the temperature -30 to pull the cord and then plug in. So they are just inside the car is heated, the car will charge wirelessly, and then they just go. Similarly, this is quite useful for physically challenged drivers also. Right? Anybody physically challenged, it is time consuming as well as inconvenient also for him or her to come out, pull the cord, and then connect and disconnect and all. So all these hassles of inconvenience due to physical challenges as well as due to the climate conditions. Okay, so that's why wireless charging is picking up. But of course, the efficiency of wireless charger is less than the plug-in charger. Okay, so when we use slow charger, I was telling up to 3.3 kilowatt, it takes 7 to 8 hours of charging. And if it is a fast charger of 100 kilowatt, it is just 20-30 minutes of charging. Okay, speed chargers of 3 to 7 kilowatt are taking around the 3 hours actually. Okay, yeah. Okay, now when this charging is done, the battery behaves differently. Okay, I mean, you cannot, why, like I was telling you that normal EV charger, we cannot use as such. We always need to use a CAN bus, communication network bus. We need to use sensors. We need to monitor the battery health. Why it is important, you can see here actually, battery characteristic. You can see that if battery charging rate, so you can see this is slow charging, which is taking 40 hours, okay, or 40 minutes suppose, or it is taking 5 hours or 5 minutes. So you can see this is fast charging and this is slow charging. Okay, so if it is slow charging, then battery voltage is quite okay. You can see this is 100%. So 100%, it is approximately 13 volt. So 12 volt batteries can go up to 13 volt, which is quite okay. Okay, but you can see if it is a fast charger, then 12 volt can go 16 volt. Or we can say that 48 volt battery voltage will go up to 64 volt. Okay, over voltage, overcharging. And what happens that this part is not called charging. You might have seen that whenever we try to pour the soda water or say Coke inside the glass, if we pour very slowly, then you can see, we'll see basically the Coke or the soda coming basically up to its full range, 98, 96 or something. If you pour it very fast, then you will see half or 60% is the liquid and the rest 30-40% is the foam. Okay, and after some time the foam will settle, and then we will see the glass is filled by only 60%. Okay, so that's why it is actually that this kind of charging is real charging. You will see that when the charge settles, it remains less. That's why we can also see it as a, like the way we discuss active power, reactive power, we can discuss is basically the real charge and the floating charge actually. That floating charge will settle, and then you will see that the battery is not fully charged actually. It was just the battery gained the voltage and we misunderstood that it has been charged. Okay, so fast charging can cause basically misconceptions or confusion of charging. Fast charging can increase the battery voltage. Fast charging can increase basically the battery temperature, and fast charging can cause basically gasification, okay, because of the high temperature of the battery. And that's why for fast charging, ventilated batteries are used. Okay, so why I was saying that that connector is important, that connector is basically monitoring all these things: battery voltage, battery temperature, any gasification, or what is the battery has reached the charge level, etc. And accordingly it changes the charging speed, or it can even cut off actually the charging. The connector is connected does not mean that vehicle is charging. Probably vehicle is not even charging at all. That communication system is making autonomous decisions by itself. Okay, yeah. So battery characteristics behave differently when the charging speed is small or charging speed is high, and that charger connectors act accordingly, making the decisions what to do. Okay, yeah. Okay, so based on the charging source, the charging type could be different. Generally, everybody works on grid to vehicle charging (G2V), and the charger is rectifier (AC to DC converter), because the grid voltage is AC and the battery voltage is DC. Okay, another possibility that I just discussed in case of e-rickshaw is solar to vehicle charging. Okay, which is very simple. What you need to use either a buck converter, boost converter, or buck boost converter, and just apply the MPPT technique. So based on, see, the solar that you put on the top of the e-rickshaw cannot give you more than 200 watt. Okay, not more than 200 watt. That's why the buck boost and buck boost or buck boost converters are good enough. Okay, and then just apply the MPPT technique. Most likely the current will not go more than 4 or 5 ampere maximum. Okay, so based on the MPPT, that charging current will be decided. That's all, and your vehicle will your vehicle battery will charge, and it can give you a higher range actually. So it is quite simple. That's why this if you study nowadays sustainable charging, so sustainable charging basically includes the renewable sources, solar and all, that can participate in the charging infrastructure and can basically reduce the power taken from the grid for the EV charging. Because suppose take the case of India, if you are charging from the grid, then it is not contributing to the carbon reduction, decarbonization or something, because in India, the 76% of the electricity or the current is coming from the coal-based generation. So if you increase basically that current for EV charging, that is somehow coming through the coal power plant, and then the carbon emission is going to the environment still. Okay, that's why in sustainable EV charging, we try to reduce in India the power taken from the grid, but from the renewable energy sources, so that you reduce the coal-based generation for EV charging application. Okay, so that's the sustainable EV charging. Another is vehicle to vehicle. Like in your hostel life, you might have noticed already that people are borrowing the vehicles of each other. Okay, and many times whenever the vehicle is out of the petrol, then we borrow basically one bottle petrol from somebody, put in our vehicle, and then go. Right? It is very common. I faced myself when I was studying. Same thing is here, vehicle to vehicle. If you are out of charge, you can just borrow charge from somebody else. But here you do not have a water, when you are not have a bottle and the pipe. Here you have a converter and the copper wire, so that from one battery charge can be transferred to another battery. Okay, so this is called DC charging, but vehicle to vehicle. Okay, here it is quite important in Western countries as well as in India, in North India, Himachal, Delhi, Uttarakhand, Kashmir, because in cold countries, the in cold weather, the battery charge leaks very fast. If your vehicle is outside, if you did not park inside the garage and maintain the 25 degrees centigrade, but if it is parked outside where the temperature is 8, 9 degrees, 0 degree, minus degree, in overnight, your battery will lose charge. And in the morning, you will not be able to start. And that is the reason in all Western countries, Dr. Kundan may know also because he studied in Italy, people use jumper. People, you have a basically a booster, the battery booster inside their car. So whenever it does not start, they just connect and then just turn the booster on, and suddenly the car will start. Okay, because it is temporary EV charging, and then after that the engine takes over. Okay, yeah. So these three kinds of charging will take place in like there are a scope for these three kind of charging. In one is common everywhere, but number two is quite important for India because our grid charging is coming from the coal, and we have basically a scope for solar in India because we are a solar rich country. Okay, so we have a lot of scope for number two. Okay, yeah. In future, you will see that people will be making a charger that can adopt everything. You can see this is my charging part. Okay, so I can connect through the grid for AC charging, and so this is AC to DC part, and then this is DC to DC part. I can connect the solar panel also, that can give me through MPPT this S2V charging, and I can connect vehicle also, so I can basically do vehicle to vehicle charging, which is DC to DC. So this is two stage. One is AC to DC stage 1, DC to DC stage 2. And you should be able to design a charger that can be connected to AC, that can be connected to solar, that can be connected to vehicle. And the modulation strategy that is required in this system, this part, should change. If it is connected to AC grid, then it should be PFC, power factor correction system. When it is connected to solar, it will be MPPT system. And when it is connected to vehicle, it is just a bulk charge for 2 seconds and then that's it. Okay, because you do not want to drain the battery of one vehicle and fill the charge into another vehicle. You do not want to do this. Okay, so it is just a bulk charging, or also known as burst charging, BURST, burst charging, just for 2 seconds or 5 seconds, and that's it. You have just borrowed 10% charge or 20% charge, and then that's it. Okay, so the modulation strategies or control strategies will change here, but a single system should be able to do all kind of charging. Okay, we have published one of our paper in that also. Not one, probably 2 or 3. Yeah. Okay. So when it comes to sorry, when it comes to AC to DC, the PFC, power fraction and power quality, is important. I mean, it should be a unity power factor mode of operation, as well as the distortion in the grid should be less than 5%. Okay, you cannot miss that. So when we talk about this 3 possibilities, as I said, that it should work as a rectifier, as a DC to DC, MPPT, or bus charging. So for individual things, we need to have a different regulations. In case of when it is grid connected, then you should have a unity power factor mode of operation, no reactive power flow, as well as the grid current distortion should be less than 5%. And it is called rectifier AC to DC. When it is solar to vehicle, then important thing is actually MPPT operation. Okay, this is the important part. And when it is vehicle to vehicle, then it is basically pulse charging or bus charging. Okay, it just happens for 5-10 seconds, and the converter can be bidirectional, probably because you are not sure how you want to do it. You want to power flow from here to here or here to here. Okay, but this is again a DC to DC converter with a pulse charging or the bus charging. Okay, yeah. Now when we talk about charging, I mean, you might have studied there are level 1 charging, level 2 charging, and level 3 charging. So I just want to tell you that level 1 charging is obsolete. Okay, level 1 charging nobody wants to do, and level 1 charging will be obsolete. The charger that will become that are coming right now are level 2 chargers minimum. Level 3 is the super fast charger actually, and the charger we are using is level 2 charger. In Singapore, we cannot buy level 1 charger at all. I think in India also, for EVs, we cannot buy level 1 charger anymore. Okay, it's level 2 and level 3, because level 1 is extremely slow and it's over. Okay, so how it works? So level 1 charger is like this basically, that always the converter output voltage is constant and charging current is decreasing continuously. So since the charging current is decreasing continuously and the voltage is constant, it will take infinite time to charge, and nobody has infinite time. Okay, right now time is the most expensive thing. All right, that's why level 2 and level 3 chargers are picking up. So you see the level 2, level 3 charging, how it happens. They do constant current charging. Okay, and what is this one? This is almost you have achieved 80% of the charging. Okay, yeah. So you can see that this is constant current charging. So you can see the converter output or charger output voltage is continuously increasing. Okay, because battery voltage is increasing when you are charging it. So if battery voltage is increasing, then converter voltage should also increase in order to maintain constant voltage difference between the two. And what is the charging current? Delta V, which is the converter output minus battery voltage divided by internal resistance of the battery. Okay, since internal resistance of the battery we consider constant. Okay, and since the battery voltage is increasing, then in order to maintain the constant charging current, converter output voltage should also increase. So the delta V, which is charger voltage minus battery voltage, should be kept constant. If it is constant, then only charging current is constant. Okay, so to make it constant, the charger voltage should be continuously increased. Okay, so and this is the problem. Okay, so this is the research problem that all of us should work. that if we do constant current charging, how to make an efficient inverter or very time sensitive and fast controlled output voltage, which is continuously increasing in order to maintain the constant current. Okay, so you need to develop a high bandwidth noise free controller. Okay, if there is a noise, you cannot increase the charging current, and if it is at low bandwidth, then it cannot be fast. So you need to develop a high bandwidth noise free controller so that converter output voltage is increasing in the same proportion as the battery voltage, so that their difference delta V is constant and charging current can be kept constant. Okay, once you have achieved this 80% of charge or 80% of the charge, okay, then you can allow the charging, then you can allow the charging voltage or output voltage to kept constant. So earlier it is called constant current mode. Now you have entered into constant voltage mode. So only two levels. And since you are in constant voltage mode, then charging current will start decreasing slowly. But 80% is quite a lot. And then whatever extra time you can keep the vehicle connected, then basically it will still keep on charging from 80% to 90 or 100%. Okay, that's what I was saying, that when you have a megawatt charger, you can allow the vehicles to go after 80% and you can have another vehicles in, or you can reduce the charging current of that vehicle and then you can give high power to or high current to another vehicle so that they can charge fast. Okay, yeah. So there is the strategies nowadays for EV charging with the two modes of operation. 80% to achieve 80% is constant current, because this can be achieved in 20 minutes. Okay, and then the rest is 10 minutes. Okay, or more, but you are allowed to go. Okay, yeah, that's why it is fast charging. Okay, so this level work chargers are basically for low power, and that's why they are obsolete now, come to completely obsolete. Okay, and you can see level 2 and level 3, which are high power charger. Okay, so you can see that these are 80 amperes. Okay, 20 kilowatt, and this is three phase 480 volt, 100 ampere and 50 kilowatt. So this is fast chargers, and this is basically level 2 medium charger, medium speed charger. Okay, similarly when it comes to DC, you can see DC level 1 is basically better than level 2, because DC level 1 itself is a fast charger. Okay, it is still a fast charger. So you can see this is 36 kilowatt, which is very fast compared to this double. So all DC levels are fast, but say 50 kilowatt, 100 kilowatt, and say 300 kilowatt, like this. So say this is taking, suppose for example, 40 minutes, 30 minutes, and 20 minutes. It's like this. Okay, yeah, or say 45 minutes, 30 minutes, and 20 minutes. So always DC are fast chargers of different levels only. Okay, AC are medium and fast. Okay, yeah, and you can see, I can share these slides if needed. You can see different companies are using basically different capacities. As I was saying, that level 1, which was very popular earlier in plug-in hybrid electric, not the full electric. As I was just saying, that full electric only level 2 and level 3. Nobody is using level 1 nowadays. Okay, yeah, you can see, as I was mentioning you, that 3.3 was very popular. Is still very popular for onboard charging because of low cost, lightweight, and high density. And after that, the single phase charger that is popular off board is 7 kilowatt, 7.2 or 7.4 kilowatt. Okay, 1.92 is level 1, which is slowly going obsolete. Okay, mainly you will see 3.3, 6.6, 7, 7.2, 7.4. Okay, yeah, and fast chargers that you can see in the range of 120 kilowatt. Okay, supercharger. Okay, used in Tesla. So these are different levels of charging actually that you can see, that different vehicles are using in different countries. Okay, in the interest of time, I will avoid this video, but I can share a link in Google Chat after I finish my lecture, so you can go through it. Okay, so now this charger is power electronics, but as you know that I was showing you here that we can develop a power converter with the grid to vehicle with PFC. So here you can see there is a diode bridge rectifier, But diode bridge rectifier is only popular for low power application. Okay, why it is popular for low power application? First of all, you do not have any control over power flow. So suppose if you want to design a high power converter, then suddenly a high power will flow as soon as you connect the charger, because you do not have any control over the diodes. Okay, like the switches. Whenever the diodes are forward biased, they start working. Okay, they start functioning. Okay, and once they start functioning, then you do not have any control over it. Although the MOSFET and IGBTs based devices, you have control over it. Another important thing that you will notice in diode is that the current that you are receiving is discontinuous. Okay, okay, here. So what happens that here, like when one pair of diode is conducting, then this voltage is passed to the output as it is, like this. And when the another pair of diode is conducting, then this negative voltage is converted to positive and passed as it is. And when you try to use a filter, then this will be the output voltage. Okay, if you use the filter. But when you think about the current, so one thing is the output current, DC current, the charging current, which is fine. Okay, which is fine. You can make it DC by using a filter. But what happens at the input? So you see that this solid one, which is this black one, is the grid voltage, because the grid voltage is coming from the grid, so it is sinusoidal. But what happens to the grid current? Okay, if you are using a diode bridge rectifier, then the grid current is non-sinusoidal, because you do not control it at all. Okay, so it is a discontinuous as well as pulsating, like this. Okay, like this, like this. Okay, now the issues that we discussed, that in case of grid to vehicle AC based charger, important thing is unity power factor mode of operation, as well as distortion should be less than 5%. But diode based charger is not able to do this. You can see that the distortion is quite high. Okay, you can see the distortion is quite high. Okay, so that's why the diode-based charger is not used. But you will be surprised to know that all e-rickshaws that are using charger, which I just showed you, and that is available in the market in 3,000 or less, they all are diode-based. Okay, that's why they become hot. That's why their efficiency is low, and that's why they, I mean, electricity bill is also high because of them, and they get become faulted very fast also. Okay, yeah. So diode based charger is not a solution, because you are not meeting the grid requirement, and you are not basically going through what we discussed, the unity power factor as well as the distortion. That's why the chargers in the market, recommended chargers by the EV manufacturing companies, the EV chargers all over the world are two-stage chargers. One is active AC to DC converter, which is also known as active front end, AFE, or PFC, power factor correction, and another is DC to DC converter followed by that. So once we are doing, so this is grid, which is AC, and we are having AC to DC converter, and then second stage is DC to DC converter. Okay, so first stage is basically the purpose is doing wave shaping, which is power factor correction. So you can see this is the grid voltage, this is the grid current. Okay, so wave shaping basically will help you to get unity power factor mode of operation, as well as distortion less than 5% or 3%, whatever you can do. You can even achieve 1% also. Okay, based on the switching frequency, based on the filter. Okay, yes. And the second stage, which is DC to DC converter, is basically adjusting the output voltage in order to get the proper level of charge, proper value of charging current. You want, if battery is 48 volt, suppose then you want to develop 60 volt. If battery is 450 volt, probably you want to develop 600 volt. Okay, so based on the battery specifications, you will either step down the voltage or step up the voltage in order to get the proper value of the battery charging current. So now the system becomes simpler, that you have two objectives, now you have two converter. One converter fulfilling the objective of distortion and unity power factor, and one converter that is followed by the PFC. That converter is basically taking care of your charging requirement as well as the battery specifications. So now the power converter design as well as control becomes very simple. Okay, very simple. Don't think that since this is two-stage converter, so efficiency will be less. No, diode-based converter has lower efficiency compared to the active front-end power factor correction-based converter. Okay, yeah. Okay, and when we talk about possible power trends, we were just discussing the diode-based converter. Similarly, when we have this AC, solar to vehicle-based system, so we, as I was saying, that buck boost converter is good enough. Okay, so since here we do not have any AC, we do not have any requirement of PFC or power unity power factor or distortion. That's why a simple switch converter is good enough, which is converting your DC to DC, because there is no requirement of wave shaping. Only MPPT is good enough. Okay, yeah. Now we are just taking advantage of this thing. So you can see that here, since the diode based rectification was causing trouble, right? No high distortion and no PFC, no unity power factor, right? So we are just combining these two technologies. Okay, so one technology which is a simple boost converter that you can use as an MPPT in S2V, solar to vehicle or sun to vehicle. Now, since you have a switch, then you can basically do the proper wave shaping. Okay, so just to see basically that whatever current, suppose this current will flow from here to here, and then when the switch is on, then we'll basically pass it on here. Okay, and when the switch is off, then this current basically will pass through the diode and go back to the load or go back to the battery. Okay, so the important thing is that now you can control the current that is going to the battery, and you can control the current that is going back to the grid. Okay, so since you are able to control the current, then you are able to buy a proper switching, because you can control the switching time of the switch, how long you want to keep it on, how long you want to keep it off. Okay, so since sinusoidal waveform is like this, right? Yeah, so you turn the switch on for a shorter time, then turn on for a longer time, then turn on for a longer time, turn on for a longer time, like this. Okay, so since you can control the battery, so you can control the conduction time of the switch, then you can control the current of the battery as well as the grid, then you are able to shape the current of the grid or the battery. Okay, that way you can control the distortion, and you can basically control the power factor also. Okay, so conduction time means with the pulse width basically. Okay, so you can see that initially you can have a small conduction time, then higher conduction time, then highest conduction time, and then again decreasing in the same manner. That way you can achieve a sinusoidal waveform. Okay, yeah. So a switch is good enough to allow you a wave shaping, but a single switch is not sufficient to allow wave shaping for high power, because switch has a limited power rating. Okay, so this is good enough suppose for 500 watt. But suppose if you want to develop a 7 kilowatt, the switch does not have the capability to transfer 7 kilowatt or to handle the conduction losses in a 7 kilowatt converter. Okay, suppose if efficiency is, for example, 95%, then 5% of 7 kilowatt is basically 350 watt. Okay, and the switch cannot handle 350 watt. Probably switch can handle only 50 watt of loss only. Okay, that's why a single switch technology of power factor correction cannot be used for high power. Then you have a different technologies like interlude system, like full bridge system, like bridgeless system, like semi bridge system, totem pole system, etc. Okay, so this is just a basic part that I'm explaining, that we can use for e-rickshaw application. Right now people are using diode based, but now we can move to this with a single switch application. Okay, now you can see that by controlling the switch time, so you switch it on, off, on, off, on, off, and based on using this kind of conduction time, we are able to achieve basically a sinusoidal grid output voltage, grid current actually. Okay, yeah, so you can see when the switch is on, which is this. Okay, you can see this is the switch current, and this is the diode current. Okay, so this current is passing through the grid, and this current is basically passing through the battery. So when the switch is on, the current basically flows through the grid, And when the switch is off, the current flows through the battery. So this is the grid current and this is the battery current. Okay. Yeah. So that way we are able to shape the current to sinusoidal, but you can see ripple. This ripple can be filtered out. So this is the inductor current. This is this inductor current. Okay. So this inductor current, when we try to unfold in two, because here this current is coming from here, one from this pair and then another from this pair. Okay. So when we unfold, this current becomes basically sinusoidal waveform. And when we put the filter, LC filter, which is low pass filter, but for high frequency, the filter requirements becomes very less for high frequency. Okay. Then you get sinusoidal waveform and you can see the distortion is quite less. Earlier when it was diode based, basically we have seen that the distortion is quite high. And this is basically low frequency harmonic. That's why the filter size is quite large. But here we are having a high frequency harmonic. Okay, low frequency harmonics are not there, so filter size becomes very less. And this way you can see we are able to achieve the unity power factor operation as well as distortion less than 5%. So the purpose to say is that you are able to do it just by using one switch, provided it is for a rickshaw or two-wheeler application where the power rating is less than 500 watt. But when the power rating increase, the single switch is not able to handle that high power to pass through because of its rating or the losses that can happen. Okay, which is say 300 watt or more. That's why we need basically different circuit topology, and this is power electronics basically. Different level of rectification, different power rating need different circuit. Okay, when we go for megawatt or 100 kilowatt, then you need basically multi-stage or multi-level systems also. Okay, yeah. Okay, so far, like I'm now just moving slowly from fundamentals to the advanced power electronics. Okay, so probably I have another 10 slides. Okay, probably another 20 minutes or 15 minutes. Okay, now everybody has worked on continuous conduction based chargers, right? I'm not sure how many of you worked on discontinuous conduction. What is DCM? DCM means discontinuous conduction mode of charger. Okay, everybody works with continuous conduction mode. What I have shown you here is also continuous conduction mode. Okay, you can see this is continuous conduction. Okay, but nobody works on discontinuous conduction because of many reasons. Okay, one reason is basically high peak current. Okay, people say that efficiency is less, but discontinuous conduction mode can help us in many ways. Me and my students, when I was in Concordia University, Canada, before moving to Singapore again, we worked on DCM based chargers and it gave us infinite benefits. Okay, yeah. See, I don't know how many of you have studied this fundamental. If you have a AC to DC converter, okay, I just say in a very simple thing. If you have a AC to DC converter, which is a rectifier and which is EV charger, right? If you apply discontinuous conduction mode, then this statement is true. Fundamental statement that source current follows the source voltage waveform if you are having a discontinuous conduction mode in AC to DC system. So what is source voltage? Source voltage is sinusoidal. Source voltage is what? Grid voltage. Grid voltage is sinusoidal voltage. If you are applying discontinuous conduction mode, then source current. What is source current? Grid current. It will follow the source voltage waveform. Means grid voltage will also be sinusoidal. Now, if it is happening automatically, that's why I have given the word natural PFC. Okay. So since if it is happening naturally, then there is no need to do wave shaping. There is no need to take care of unity power factor. Only thing you need to take care is basically the distortion part. Okay. This is one thing. I mean, your many problems will be solved. Another thing is that there is no need to do synchronization of the grid voltage and grid current. Okay. No phase lock loop required. Zero crossing detection. And since there is no synchronization requirement, so the complexity of the system will be reduced. And one major benefit that we received, that this is single sensor, single loop control. Okay, you can see like this. Okay, generally people use minimum two sensors, maybe three, but minimum two. One is the input current to wave shape, another is the output voltage in order to regulate the output voltage. Okay, so that you can maintain constant current or constant voltage mode. Okay, but here, since input current follows the source current follows the source voltage waveform, and because of that we do not need the input current sensor. Okay, and because of that we do not need a two loop control, because input current is automatically getting controlled, and our full focus is basically on the battery charging current, which depends upon the output voltage of the converter or the charger or the rectifier. Okay, then our control becomes a single loop control. We need only one PI control to take care. We need only one error to rectify, and then the hardware and software requirements becomes quite relaxed, quite simple, and the control becomes very robust. And since we are using a DCM mode of control, so in DCM what happens that the inductor size, the boost inductor size becomes very small. Then only you will achieve DC. If you want to achieve CCM, then inductor should be large. Okay, if you want to achieve DCM, then inductor should be small. So if inductor size becomes very small, then we know very well that inductor comes with the magnetics, the ferrite. And the magnetics is expensive, magnetics is heavy, and magnetics takes more space in the power converter. So once inductor volume is inductor size is reduced or inductor value is reduced, there is cost, volume, and weight is also reduced. So we get another benefit of, in addition to simple control, we get a benefit of high density, low cost, and low weight system also. Okay, so just using DCM technology, we got all these merits actually. Okay, yeah, and since India we is using basically 48-volt electric vehicle, so you cannot go for diode based rectification at the output here, like this diode. You cannot use a diode here, or here you cannot use in DC to DC converter, you cannot use the diode. Okay, because a diode based rectification will cause basically high losses. For example, if it is a 1.5 voltage drop across the diode, so if you are using basically, suppose one diode like a boost converter, and suppose the rating is 500 watt. Okay, if output voltage is 50, just for simplicity purpose, then current is 10 ampere, and 10 multiplied by 1.5 is basically 15 watt. Okay, which is approximately 3% loss. Okay, at higher voltage, high power, it will be more. But if you use basically synchronous rectification, means if the rectification is done through the MOSFET rather than the diode, then what happens? 10 square I square multiplied by R. And what is R? R is 3 million, which is 0.003. Okay, so 10 square is 100. 100 multiplied by 0.003. This becomes basically 0.3 watt. Okay, so you can see basically 3% loss versus basically 0.1% loss. So you can see that for low voltage application, we do not use diode rectification, but we use synchronous rectification in order to obtain high efficiency. And high efficiency means less losses. Less losses means less cooling requirement, less heat sink size, that can again save on the cost, volume, and the weight. Okay, that's why since our EVs in India are basically 48-volt based battery based vehicles as well as e-rickshaw, so we have scope for designing a synchronous rectification based EV charger that can obtain higher efficiency. At least for 500 watt, you can save 3%. When it goes for high power, you can significant energy you can save, multiply by 23 crores of vehicles, and it becomes very significant actually, gigawatt. Okay, if you try to do the study. Okay, so synchronous rectification based EV chargers opens scope for us in India. Okay. Okay, now another thing that people use, I was just showing you earlier the boost converter based PFC, which is quite popular. Nobody has done earlier, but basically we have shown that buck boost converter can also achieve PFC. Okay, and we use basically DCM only. You can see when the switch is on. So this system is basically buck boost, right? Instead of boost. Boost converter has an inductor here and switch here. And we have a inductor here and switch here becomes buck boost. And when the You can see like this switch is on, inductor is storing energy. When the switch is off, inductor basically delivering energy. And this is discontinuous conduction mode. Both are off. There is no current basically in the inductor. That's why this is discontinuous conduction mode. Okay. Yeah. So we have demonstrated it using buck boost based PFC also, directly buck boost as well as through through interleaved also. So you can see we use directly a simple buck boost converter, and we have used basically DCM. You can see that DCM has three modes: on, off, and basically no power. Okay. So we have done it through buck boost converter directly, and it is AC to DC. This is AC and this is DC. Okay. And we have done it using a variable voltage. For example, 240 volt can become 280, it can become 270. Since it is a 48 volt battery, so we are using a charging voltage of 65 volt, and we tested it for 3.3 kilowatt, 50 kilohertz switching frequency, because we implemented hard switching for now. But since it is a DCM, so it is achieving GCS, zero current switching. And these are the devices we used. Okay. Yeah. Okay, my students, you will not believe, these were master's student, and they developed the prototype which is equivalent to industry standard. You can see it is always maintaining unity power factor mode of operation. So this is AC and grid voltage and grid current, and you can see this is output voltage and output current, which is DC. Ripple here is less than 5%, and distortion here is basically less than 5%, 4.89%, and power factor is close to unity. Okay. Yeah. Later on, the same group of students basically they do they have basically demonstrated using for high power. So you can see instead of one power converter at the input, they are using two power converter. So it is called basically interleaved. High power, so power is divided into one switch, one inductor, and another switch, another inductor, half and half, so that you can double the power. And basically, since we are using 48 volt battery, and since this is a 240 volt, and then what is happening? We are using a half bridge at the input, so that the voltage becomes half. So this 240 becomes basically 120, and this 120 volt basically can further reduced by this transformer turns ratio, or a center tap transformer to half. This 120 becomes basically 60, and that is basically charging the 48 volt battery. Okay. And you can see instead of diode, we are using switches on the secondary side, and that is causing synchronous rectification. So you can see that like a full bridge converter, we are using a divider. So it has a two switch at the input, and we are using a center tap transformer to reduce the voltage. And again, you can see there are two switches at the output. So number of semiconductor devices are also quite less. Okay. And again, you can see that the students develop an industry, master's student again develop the industry standard prototype. The student received the best thesis award in Concordia University at the university level. That is called F.A. Gerard Master's Dissertation Prize. Very impactful, very valuable award. And the student also received the best thesis award from IEEE. So student basically utilize the top place as well as the bottom place in order to make high density compact power converter. And you can see the unity power factor mode of operation using interleaved buck boost DC. So you can see that here also it is quite good waveform, but because it is an interleaved system, so you can see the current waveform is better because of the ripple cancellation. Okay, this is the DC output voltage, but this is AC input and AC current. Unity power factor mode of operation, you can see distortion is less than 4% because of the ripple cancellation. And you can see the charging current is reduced to half. So you can see this is the grid current is reduced to half, but it is still stable. Okay, still unity power factor is still one cycle control. Immediately from one to another change, it is very fast, very instant. It does not go out of the synchronism because of the DCM. Similarly, you can see the current from less is going to high. You can see they are still in synchronism. Okay. See here. Because of this, we received very high efficiency. You can see in the range of 96, 97, even in our laboratory. Probably the industry, we received 96, industry probably can do 97 also. Okay. When we compare this with the many state-of-the-art technologies, so you can read our paper. So these were master's student and they published basically 2 IEEE transactions because they really demonstrated high performance, high impactful results with just DCA mode of operation with 2 different topologies, with synchronous rectification and without. Okay, yeah, and you can see this. So this is a part of our paper. Students did a benchmarking with the different papers, which are using DCM and which are using basically CCM. Okay, and we demonstrated basically quite high efficiency from full load to light load application. Okay, and no PLL requirement, very simple control. Semiconductor voltage is high because of the buck boost converter rather than the boost converter, and current stress is low because of the interleaving system, and total switches are 6. Okay, and yeah, I mean, this is just a benchmarking that students did finally. Okay. So this DCM operation, if we try to adopt in 3-phase system, you can also do in 3-phase. In 3-phase, 2 sensors in 1 phase, so total becomes 6 sensors. But if it is a DCM, you can just move to single system, single sensor, which is basically output DC voltage. Because output voltage is just 1 DC voltage, but input voltage and input currents are 3. That's why 6 sensors. So that significantly reduces the cost. Okay, only 1 loop control even in 3-phase system. Okay, yeah, and again it is a natural PFC with single sensor, single loop, making the system much easier when it comes to 3-phase. Okay, so you can see if people use a normal CCM based charging, you see 3 current sensors or 2 current and 2 voltage sensors and 1 voltage sensors here, at least 5. Okay, but when it comes to discontinuous conduction MOS base, only a output voltage control, like that when we just discussed here, everything is natural. Okay, that makes the system quite simple and easy. Okay, because of the interest of time, I did not put the results here, but if you go online and if you search the thesis of my student Siva Nagaraju Gangavarapu, okay, he was my PhD at Concordia, and his thesis is available online freely. Okay, then you will see the results for 3-phase converter also that we use for aircraft application. Okay. Okay, so just to conclude that we have basically a wide variety of chargers possibility. All have potentials, but it depends upon your requirement, your convenience, your specifications, your applications, and the circumstances what you want to use. Okay, nothing is good, nothing is bad. But we have seen that PFC and distortion is very important for AC based charging, which are the majority of the chargers, because you cannot rely upon solar all the time. Okay, and when we use basically non-traditional PFC system, which is discontinuous conduction mode, and we have received that there are many benefits, and I demonstrated you through experimental results that a single loop simple control, single sensor simple control, and a smaller inductor cost, size, and volume based power factor correction is possible just by using DC. Okay, yeah. So thank you very much for patiently listening. So I think we have 15 minutes, and we'll be happy to take any questions.
So participants are requested. Kindly you ask the question from Professor Akshay Rathore. Sure. Sir, one question from my side.
Uh-huh.
You have used a boost converter, right? And buck boost converter for the power factor improvement in case of the simple rectifier circuit, right? So in place of that, can we use other converters? This is such as cuck converter is there, and so many other topologies are also there. So
Yes. Definitely we can use. I mean, only thing is that what can make simple from implementation point of view,
yeah,
that can require less number of switches, less number of passive components, inductor and capacitor, because those are expensive and volume intensive. Yeah,
mm,
and that can cause a simple control of operation, because buck boost are quite simpler in operation compared to say cook converter or septic converter. Yeah, because it is just on and off, but and only one inductor, one capacitor. But in the other topologies, which can make sense also, I'm not denying, but the important thing is the simplicity of operation that can make sense for that particular application from implementation point of view.
okay. Sir, is there any possibility to bidirectional charging, because capacitor is there, and
Yeah. So
uh,
bidirectional charging, like if we see that whenever we try to do vehicle to vehicle, as well as whenever we try to do vehicle to grid. Right
grid?
now, we have a $3.6 million project in Singapore, my team, to develop a vehicle to grid test bed in Singapore. And currently, we are working on that, basically, that how we can achieve for a single vehicle or for a fleet of vehicle, aggregate all the nodes and then inject power to the grid. So right now we are working on that. And that requires basically a bidirectional power converter with proper power flow control.
Okay.
Yeah, because grid to vehicle is charger and vehicle to grid is basically discharging the battery. So these are two different phenomena, and different phenomena, not only, I mean, in terms of power flow, but battery charging rate and battery discharging rate, because that controls the battery temperature, that controls the battery health parameters and more actually. Yeah, so whenever we design, we really take care of this battery part, because charger is not expensive, the battery replacement is quite expensive, battery maintenance is quite expensive. So designing bidirectional charger is not challenging. I mean, if you see the UPS system, right, the UPS system is bidirectional. You basically, I mean, you charge the battery and then you discharge the battery actually. Yeah, but here the important thing is this battery health part, so not the power converter part. So right now, whenever we want to use the batteries as the virtual power, the electric vehicle battery as a virtual power plant, or as a grid energy storage, or as a emergency backup power unit, then the charger can be used as a inverter or as a UPS, and then we can use that power to support the grid or support to house standalone in a standalone way. So there is a scope for that, and then people are working on V2G.
Okay.
Sir, some question from the participant
Mhm.
in the chat box. I'll read that one. Pawan Kumar, what is the advantage of two-stage?
Yeah, so basically, as I was mentioning that in two stage, the control is better. The one stage is controlling the power factor correction for the grid, as well as the total harmonic distortion in the grid current. And the second stage is basically controlling the charging current, which is DC to DC converter. So the objectives are divided between the two systems. If it is a single, basically, then one single converter has to fulfill all the objectives for the grid side also, for the battery side also. But in two stage, one stage is fulfilling the objectives of the grid, the second stage is fulfilling the objective of the batteries. So things becomes very simple actually. That's why everywhere we are using two-stage control. You will not see a single stage, two-stage charger. You will not see a single stage charging system anymore.
And uh, one question, Narayana Mathur, for the design totem pole PFC, which controller was used? Is it a programmed PFC controller IC?
Yeah. So basically, what happens that people who are designing for standard specifications and for general specification, which is standards, as well as for a low power system, low power application, then a dedicated PFC controller IC is available actually. But when it comes to a non-traditional specifications of the batteries and high power application, then you have to design your own actually. Then it is a user programmable system rather than you are using a PFC controller IC. This is just feasible. This is a feasible part for low power application.
And with this, he also asked, kindly explain the hardware setup and the component selection in the totem pole PFC.
Yeah, so hardware setup and component selection comes from the design. Okay. I mean, there is no general explanation. So you have to go through the mathematics. You have to go through the modes of operation, like different mode of operation will give you the value of the components rating. Components rating. And the equations basically will tell you the value of the current that those components needs to withstand. Okay, so from those design equations and from those mode of operations, you will get the values, V and I values, as well as from when you multiply them, then you will get the KVA rating. VA rating, V into I becomes VA, KVA rating. Then only you will be able to select the components from the available list from the say the DG key or from the mouser, etc. Okay, so there is not a standard value for totem pole something. Whenever the specifications are there, voltage, current, and frequency specification, power specifications, okay, then you have to follow the mode of operation and equations to come to the ratings, voltage and current, and the VA rating. And then from the available list of components, you select actually.
And another question is, fast charging create minimize mileage of vehicle?
It's not about vehicle, it's about the battery. So what happens that when you charge the battery very fast, then the battery dielectric or battery material degrades. And because of that, basically battery loses its capacity, its strength. So right now, if battery is able to supply, suppose 300 miles, then after battery material degrades, it will be able to supply 240 miles. Then after some time, battery will be able to supply 180 miles. Then you will feel that, okay, my battery is not enough to give me the enough mileage. That's why you have heard about another term, second life of the battery. Then you remove the battery from the vehicle and use it as a UPS for the energy storage or for the backup power application, and which is for your house or for your clinics or for your shops, etc. And then for your vehicle, you use basically another brand new battery that starts its life again and then can give you the longer mileage. But purpose to say here is that mileage is affected, but the battery life is not over. You can replace the application from transportation from the dynamic to stationary backup power supply or energy storage application like UPS.
And another, is there any development worldwide in the standardization of chargers?
Yeah, so this is one area basically of interest because Europe, the standards are different. US was using the Tesla standards. In Europe, they were using CCS2 chargers. And in China, they were using something else. So now, in order to offer the roaming solutions, now they are really working. Suppose right now in our V2G project, we were about to buy a charger, but that charger does not fit the standards or the regulation that our energy market authority or our grid has decided. So we were not able to buy those. So everyone is working on the common standards so that they can sell the chargers to the international market. Otherwise, their market is limited. Okay, if my standards are different, European standards are different, Japanese standards are different, Americans are different, Indians are different, then you do not have a global charger that you can sell everywhere. Okay, that's why the manufacturers are working on common standards so that Hyundai can sell its EV and chargers in India, in Singapore, in Australia, and worldwide. Okay, so this is one major subject of interest currently for chargers as well as for batteries also. How to dispose the batteries, how to do the second life of the batteries, how to use battery chargers, EV chargers into UPS chargers later. All these are basically opening scope for standards so that every product can be a global product from the selling and the business point of view.
And one question from Prasad Kulkarni, please give some insights on model predictive control in converters of EV.
model predictive control, probably for traction power, you do not want to use probably from the traction power. I mean, there are 2-3 power converters in EVs. One is the traction inverter, another is DC to DC converter, which is giving power to the fan, Bluetooth, entertainment system, air conditioning, lighting, etc. Okay, that is quite low power and converting that battery voltage to 12 volt. Okay, so that is not, I mean, of high interest because it is quite reliable. Another is traction inverter, where again you do not want to use model predictive control because a standard space vector modulation or vector control is good enough to control the inverter voltage and current, variable voltage, variable frequency, in order to control the speed of the vehicle. Okay, and regenerative braking to feed power back in, which is quite standard. Power MPC probably you can use into EV charger, or MPC technology you can use basically to know the current health of the battery, or current health of the traction inverter, or current health of the charger basically. Okay, because once you have a model, and once you have the accurate model, then you can basically use sensors and transfer the data, where you can see what is the current health of the battery, what is the current degradation of the battery, current state of charge of the battery, current temperature of the battery, or in the inverter part, what components are reaching their limit and they will require maintenance or replacement very soon. So rather than your vehicles stuck somewhere, you know the way, you know basically that it is the time to replace those component, or replace the inverter, or replace the battery sensor, etc. So there you see basically the scope of model predictive control. Same thing for the charger. I mean, you are doing a fast charging to the battery. Okay, now suddenly you realize that because of environment, in summer the battery temperature becomes high very fast, but in the cold environment the battery temperature will not rise that fast. I mean, there is difference between the two. Or in Kashmir or Himachal, it will not rise very fast because already the surrounding is cold. But in say Tamil Nadu, Rajasthan, Maharashtra, it becomes very fast because surrounding is already 48 degrees. Okay, so model predictive control basically, when you are doing a charge, so that model predictive control can provide you the value that battery temperature has basically increased quite a large value. So you are not supposed to inject power further, because if you remember my slide, I was telling you that 80% you can do by constant current charging, fast charging. But if battery temperature has reached to its high value or maximum limit, but your battery is only charged 60%, then you have to cut it off. You cannot wait for another 80%, otherwise your battery will explode. So many times, I mean, a few days back, there was a news also that a scooty was basically connected, and there was a blast, and there was a fire in the house. 2-3 people, including 2 kids, died. Okay, so this kind of situation can be avoided by this model predictive control. Okay, yeah. That is now another term is coming, health conscious charging, using this model predictive control system.
And one more question: what role do supercapacitor and battery technology play in revolutionizing EV charging?
So basically, these are just complementing each other. Okay, why we use battery? Because battery energy density is quite high. It means in order to go for a large range, the volume and the weight requirement is less if you use the battery. But if you use supercapacitor instead of battery, then the volume and weight requirement will be quite large actually, because supercapacitor energy density is very less, but supercapacitor power density is quite high. Power density and energy density are two different terms. Okay, energy density means energy storage. You can go these many miles. Power density means what is the peak power you can transfer. Okay, so the peak power that you can transfer is higher basically from the supercapacitor, but that is not constant all the time, right? You basically do peak power only when you are at highways, but when you are doing city driving, you are not having a peak power at all. Okay, so people have published papers where you can see the hybrid technology. People use battery plus supercapacitor. Whenever they are on highways, they can switch to the supercapacitor. Whenever they are doing regenerative braking, they can send power to the supercapacitor rather than the battery, and using the battery during the urban drive actually. Okay, the purpose is to maximize the battery lifetime, The purpose is to capture the relative power to the supercapacitor. The purpose is to supply acceleration power from the supercapacitor rather than the battery, so that the battery temperature is within limit, battery health is better. So the purpose of complementing through supercapacitor is to basically, one thing is the enhancing the range as well as enhancing the battery life. Okay, but market is cost driven. Market is basically the uh, driven by the less maintenance, less failure, uh, overall less life cycle cost. Actually, that's the market driven. That's why this concept, although published and demonstrated in literature, it is not picking up in the actual practice. Okay, using two storage increase the cost. Using two storage, you need basically two sensors and control strategies. Then the reliability goes down. Basically, anyone can fail. Okay, and if anyone can fail, then you have to restore it to something that also you need to plan in advance. Okay, that's why this is not picking up. Although from publication point of view, from the proof of concept point of view, you can see many publications in this area.
And one last question, kindly highlights on the following: high frequency transformer selection in the charger and use of SIC or GAN switches in driver circuit.
Yeah, so SIC is basically for high power application. Suppose if you want to go for fast chargers, 50 kilowatt and more, then we use silicon carbide charger, silicon carbide devices. But if our charger is 7 kilowatt or less, which is single phase, then we use gallium nitride device, because gallium nitride devices are coming for low voltage, low power application. Silicon carbide devices are coming for high voltage, high power application. So level 3 chargers, fast chargers are silicon carbide based, and level 2 chargers and medium speed chargers are basically gallium nitride based. Okay, driver circuit is challenging. Okay, driver circuit of silicon devices you cannot use in silicon carbide or gallium nitride devices because of the different switching speed, because of the different characteristics. Okay, many companies like Infineon, like Semicron, like Wolf Speed, they have developed basically their dedicated chargers. So nowadays, those companies are recommending that if you are using our devices, better to use our drivers, including that ST microelectronics also. Okay, you use our drivers because these are dedicated drivers for our devices only. Okay, right now what we do in silicon, you choose your driver of your choice for any silicon device. Okay, but this is not possible for gallium nitride and silicon carbide because of their different characteristics, different parasitics, different temperatures, different peripheral, different temperature selections. Okay, different dV by dt. That's why dedicated drivers are coming from the same manufacturers also. If you use different one, you will see the performance is not up to the highest level, because important thing is to unlock the potentials of these devices at their maximum. And that is only possible if we use basically the dedicated drivers for those devices. Okay, so this is completely a different area where the industries are working for making drivers for their own devices. Okay, high frequency transformer selection, I mean, you will see different categories. One is simple ferrite core, which is still popular, but low cost, but volume is more. Nowadays, people are using planar transformer, which are basically quite sleek actually. So the volume is volume is less, weight is less. And another is basically nanocrystalline core transformer, where the core losses are very low and you can get very high efficiency. And the core volume is also quite low for high flux value. Okay, so you can go for high power, high flux, basically even in a smaller core actually, nanocrystalline core transformer, but the cost is a bit high. Okay, cost is a bit high. So it is up to us basically that how we want to bring. If you want to go for high efficiency, people can use nanocrystalline core. If you want to go for low cost system, then you want to use ferrite core. If you want to make a compromise between the two, then you want to use basically planar core transformer.
Okay, sir.
Thank you, sir, for enriching us with your valuable words and esteemed presence.
Okay, on the behalf of organizing team, I extend my heartfelt gratitude to our esteemed expert for delivering insightful and engaging lecture on electric vehicle charging process. Your in-depth explanation of the technical aspects and practical challenges such as battery charging time, overcharging risk, factor affecting charging speed, and use of boost and buck boost and interleave PFC converter for diode rectifier, advantage of to operate converter in DCM mode has provided the participants with deep understanding of this critical area. We sincerely thank you for sharing your time, insight, and experience. We look forward to continue collaboration and learning in this transformative field. Thank you, sir. Thank you.
Yeah, thank you very much. I shared my email address. In case you have any
Uh,
queries later on, feel free to send me. I will be happy to answer. Usually I reply very fast.
okay. Thank you, sir.
Thank you, sir.
Okay, thank you everyone. I will just log off now.
Yes.